Today, I'll be covering Hugging Face's Deep Reinforcement Learning Unit 2, which is centered on an introduction to Q learning. So, there are two types of value-based functions. We have the state value function, which outputs the expected return if the agent starts at a given state and acts according to the policy forever after. We have our action value function, which outputs the expected return if the agent starts in a given state, takes a given action at that state, and then acts accordingly to the policy forever. The big distinction is that in the first one, agent starts at a given state and acts according to the policy forever after. And in the second instance, agent starts in a given state, takes a given action at that state, and then acts accordingly to the policy forever after. In value-based methods, rather than learning the policy, we define the policy by hand and we learn a value function. If we have an optimal value function, we will have an optimal policy. So some of the diagrams that are in the course that describe this. The first one, state value function. We have the value of state is equal to the expected return using the policy to choose its actions for all time steps. For each state, so G, T is return, the state value function outputs the expected return if the agent starts in that state. If agent starts at that state, if state is equal to small s, value of state s, if the state of the agent, if our agent starts at state s, and then follows the policy forever after. This picture demonstrates this. Oops. So you can see that we calculate the value of a state at each state. So in this state, we are at -7. Here we're -6. If you go down, you go -7. You go down, -8. You can see that your value of that state is decreasing, which is not good. No bad reward, bad reinforcement learning agent. So if you keep going down, maybe instead of at this intersection, instead of going and taking a right, you continue, or going down, you continue going right. You'll get a higher state. So -5 is greater than -6. And then you can see go right again, -4, down, -3, down, -2, right, -1, and then you get to the end goal, which is the cheese. To contrast this, we'll take a look at the action value function. And the big difference, like I had mentioned, is that in the action value function, you take into account the agent starts at a given state, takes a given action at that state, and then acts according to the policy forever after. So the distinction is that action. The function is defined as the value of the state action. So for each state action, the action value function outputs value of state action pair with state and action, the expected return, and then pi is our policy, and uses the policy to choose its action for all time steps. And if the agent starts in that state, and takes the action at that time step is equal to action, and then follows the policy forever after. And how this is depicted is that on here, this chart contrasted with the other chart, you can see that one of the big caveats first is that they didn't fill all the state action pair for the example, because it would be a whole 4 numbers per each one of these boxes. We're only showing the value of state action pair. So you're in the state and the action is to go to the right, that has a value of -7. If you're in this state and the action is to the right, it has a value of -6, -5. But if all these ones are going to the right, and you see here, instead of like there'd be pretty much, you can't even go to the right anymore, but going down, there's a value of -4, going down -3, going to the right at this state -2, going right at this state -1, and then you get to the cheese, our goal. So those are the two types of value-based methods. And as a recap, in value-based methods, rather than learning the policy, we define the policy by hand and we learn a value function. If we have an optimal value function, we will have an optimal policy. So the secret is trying to get these numbers with enough training to be the optimal in the grand scheme of things. Now, there are two types of methods to update the value function. With the Monte Carlo method, we update the value function from a complete episode, and so we use the actual discounted return of this episode. You can see in the diagram, the AI goes the entire training run. So I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 takes 10 actions, 10 steps, and that's what they consider the time the end of the episode. And it's only after the completion of the episode that the learning occurs, where you update your value function. Now contrast this with the temporal difference. TD is temporal difference learning method. We update the value function from a step, replacing the unknown g of t with an estimated return called the TD temporal difference target. You can look more into detail on that, but succinctly put, you learn at each step instead of having to wait until the very end of the episode. So temporal difference is difference between next step and the step after that, but the learning occurs at each step. These are just two types of methods to update your value function. Now we're introduced to this concept of Q-learning. So Q-learning trains a Q function. It's an algorithm that trains a Q function, which is an action value function encoded in internal memory by a Q table containing all the state action pair values. Given a state and action, our Q function will search its Q table for the corresponding value. So you can see that we'll take a state and an action, we'll put them into our Q table using the Q function. So each state action will have a numerical value, kind of like here, -7, -6, -5, or over here, -7, -6, -7, -8. And we will derive the Q value from our Q table dependent on the state and action. So when training is done, we have an optimal Q function, or equivalently an optimal Q table. And if we have an optimal Q function, we have an optimal policy, since we know for each state the best action to take. The formula for what this is describing is the policy star of state is equal to the max of the max Q of that state action pair. Finding an optimal value function leads to having an optimal policy. So in the beginning, our Q table will be useless since it gives arbitrary values for each state action pair. Most of the time, we initialize the Q table to 0 values. Looking quickly at this diagram, you can see on the left we have our initial Q table, and after training, the Q table, the numbers change because we have now gotten state action and we have added a value to each state action. So you can see if the state is at the mouse, you want to go left. If you go left, 0 value. If you go right, that has a value of 10.8. If you go up, has a value of 0. Going down, value of 0. If you are at the cheese, you go left 0, right 9.9, up 0, down -10. These are the values for the state action at that state. So you can see that an example is if you're at the cheese, the state is a cheese. You go left, you get 0 reward. If you go right, you get 9.9 reward. If you go up, you get 0 reward. And if you go down, you get -10. So not good. But as we explore the environment and update our Q table, it will give us a better and better approximation. So how this training works is that at the end, or like temporal differently, you can update the value at a given state action pair. So, and then when you rerun the training, you can update those values furthermore based on the outcome of that state action and that run. And lastly, this is the algorithm for Q learning. It looks complicated, but it really is simple. They have a good example of what it is broken down, and I'll go include that real quick. So actually, I think it'd be better to just go into the example now. So I'll be breaking into the hands-on example. So you can open up Colab. The link is the hands-on course, the hands-on section of the Unit 2 section. And you can see here, we give some of the examples, give you a preface for what you're going to be training. We'll be starting off in the frozen lake scenario, and then eventually we'll be going into this taxi scenario. The frozen lake scenario, I'll just briefly go over it. They give a good recap, and now you can start off with the actual code execution. So we're just getting our environment ready. I already went through and I saw that you don't need to have GPU acceleration on this specific notebook. So we can go and omit that step because all of the training apparently can be done on CPU instead. Maybe take longer if you do it on CPU, so I might change the runtime. So let's just go do that. All right, go rerun the command. Basically, you'll go and install your requirements, update your environment. You have to go kill your notebook and restart it so that you ensure you actually use the libraries you just installed. You will go and create the display. You will declare it as non-visible for the beginning because you don't really need to see the training runs, but you can turn it on if you want. Then you import the packages you're going to use: NumPy, Gymnasium, Reinforcement Learning Library, Random, so we can take random actions as part of our training, ImageIO, OS, TQDM, Pickle5, Notebook. Don't know really what those ones do, but we can go explore it. So in the environment, the first environment, part 1, we start off in the frozen lake environment. And you can see that we create an environment and you have to add some parameters. So the parameters in the solution are you put the name, and you can, I'm more used to like cursor, but generally you can go control space and see what are the actual parameters you can set. So you can set the name, the map name, check if it's slippery, and then render the render mode RGB array, which is a single frame representation of the current state of environment A. A frame is a np.nd array with shape xy3 representing RGB values for x by y pixel image. So succinctly put, you're just creating your environment, your training environment. And then you can go print what your environment is. You would see if you ran this that you would get the observation space, which I think is, well, it says right here, you can have 16 possible observations. Since there's 4 by 4, you can have this observation, this one, this one, this one, and all the these ice holes. And then get a random observation, and you would just get a random number from that observation. And then if you take a look at the action space, you can only do 4 different actions. You can go left, down, right, or up. And the reward function is if you reach the goal, you get +1. If you reach a hole, 0. And if you reach frozen, 0. So basically, you only get a reward for getting the goal. So now we're looking back at the Q learning algorithm. And one of the things that I saw is after going through this workbook is that this algorithm is much more simple. Like it looks more simple when you're actually typing it, coding it out, because the library already kind of handles a bunch of the stuff that you do, so you don't have to write it out in like natural language, which is not even natural language, but in like formulaic algorithmic expression notation or whatever this is called. Let's see. So going back on topic, the next steps here are we can define what the state space is and what the action space is. And the state space is what are all the different states in this environment and what are all the different actions. And if you ran that, you would see, let's see. Looks like I can't get the number off the top because it's not printed out. But if I were to have ran and executed every block of this notebook, you'd be able to see how many states there are and how many actions there are. Possible states, possible actions. And to create your Q table of the size of state space and action space, so if you look back at the table, it is basically states on one axis and then on the each new row, and each column is the action of that state. So it is a pretty like intuitive table. So you create a table which will have a state space and an action space, and you initialize each value at 0 using np.zeros. So numpy zeros, you set everything to 0 in the state space and action space, and then you return the table. And if you run this command, you would execute your initialized Q table with your state space and action space as parameters that you would have defined in your environment. Well, you would have derived from your environment. Next, the greedy policy. So what the greedy policy is an off policy algorithm that is used for specifically updating the policy. So the epsilon greedy policy is the acting policy, and the greedy policy is responsible for updating the policy. What off policy means is that these two policies are different. The acting policy and actually updating the policy are different policies. I use the word a bunch, but off policy using a different policy for acting and for updating, and then on policy uses the same policy for acting and updating. And these are from these the deriving the value for the state action pair, since this is kind of utilizing that value based method as kind of part of this Q learning algorithm. So we would define the greedy policy is in this block, which we would define as the max of the inner table getting the state at that action, the highest action at that state. So kind of if you look at this equation, max Q at S at state, the next state plus action, this is the greedy policy. It's put it looks pretty much exactly the same when you write it out in Python code, utilizing the NumPy package. So this is simply defining the action you take is going to be the maximum of that state. So looking at the state table again. So here, if we're at this cheese, where the state is this cheese, we have 4 different possible actions. the action we would use per the greedy policy is 9.9, since it is the highest value for that state action pair, or for that state out of all the possible actions. You wouldn't want to do minus 10 or 0 as your action if there's an action that you know has a higher reward. So going back to ours, defining the greedy policy, you get the max action at that state in your Q table. Next, we would define the epsilon greedy policy. This policy handles the exploration exploitation trade-off. So in Unit 1, we learned that there's a trade-off between going and exploring your environment more in a training run versus going and exploiting the reward earlier on. So you would, if we were more exploitative, we would not do any exploring, since you would just stay at that state, go to that state action that has that high value already. But if you define this policy to maybe like there's like two numbers with probability 1 minus epsilon, we do exploitation, and at probability epsilon, we do exploration. So what that looks like in practice is you would randomly generate a number between 0 and 1. So this is kind of like getting it's random under the hood. And if that random number is greater than epsilon, you would go for more exploiting that reward. So take the action with the highest value given a state, and NumPy argmax can be useful here. So action, we are now using our greedy policy, passing our Q table and the state we're currently in. And if you go take a look at our greedy policy, we would pass Q table and state, and we would take the action with the highest value of that state action pair. And if not, if that random number is less than epsilon, then your action would be action space dot sample. So you would take a random action. And by random action, those random actions over time will, like you're exploring, like maybe you go up when instead of going right, or you go down and you go to a new state, which has their own set of action values for that state. And you can see how with each time step, this will keep on updating and updating your Q table. And then you go to the next step, next state, because you have taken another action, and then you got derived a value from it. So when you define your epsilon greedy policy, you're tackling that problem of exploitation versus exploration. Now, we will define the hyperparameters. So this is kind of where like all those variables that you see in the Q-learning algorithm, you kind of just plug and play based on whatever you kind of decide is optimal. And you can try a whole bunch of different numbers. Here they give an example. We'll just use 10,000 training episodes. We'll have a learning rate of 0.7. So you can see in the algorithm that this here, alpha, is the learning rate. And changing this number will impact the actual value of that state action pair. So changing it will have, changing this variable has an impact on your end state. So it's one of those variables that you can test to, you can switch up to see what the different outcomes are for different learning rates. And potentially, like maybe you'll find a better learning rate for an environment. But here we will use the learning rate of 0.7. You can see how many number of total test episodes for your evaluation. And then here you just set your environment, how many steps, max steps per episode, the gamma, which is the discounting rate, the seed of the environment, max epsilon, min epsilon, decay rate. So exploration probability at the start, minimum exploration probability, and exponential decay rate for exploration probability. So you can see here we set a min and max, and going back to our epsilon greedy policy, that's where if that random number is greater than epsilon, you do the greedy, you exploit, or else if it's less, you will go and explore. So take random action. And this is the exponential decay rate for exploration probability. So you will decay 0.0005 as you continue progressing in your training episode. Now we create the training loop method. The training loop method kind of looks like this. For episode in total of training episodes, we reduce epsilon since we need less and less exploration, then reset the environment. And for step in max time steps, so this is now, you're going to loop. So this is a for loop. Choose the action choose the action A of action at time step using epsilon greedy policy. Take the action A and observe the outcome state S and reward R. Update the Q value. So Q at state action pair using the Bellman equation, which is that value plus learning rate times the reward at state action plus gamma that you defined earlier times the max state minus the estimated state. And if done, finish the episode, or next state is the new state. So you convert that kind of pseudocode into actual code in here, which ultimately will look something like this. But you can see that you turn that formula and plug and play our values from the environment, and it's all kind of starts to click. So nothing in here is different than in this pseudocode right here. We just plug in our variables based on the work we've done so far in this workbook. After you complete that step, you define how you're going to train. You go and execute that command and pass in the variables you have set up in your training parameters. And I've already done that, so I can show you how mine looks like. Go into my profile, and the first one was this frozen lake. So everything that you saw in this collab, this is the output, and you get a cool video that shows you starting in this state, and after your training runs on without even having to control go down, go down, go right, go down, it learned on its own using Q learning how to go to our goal, which is the goal. They defined it as goal, and you get a reward +1 if you get to that state. So without having to do any training on my own and just running this code, I'm able to go from point A to point B while avoiding these hazards. These are frozen lakes or whatever they are, the holes. And the same is pretty much done for the next example, which is taxi, but it's a little bit more advanced since we have to, instead of just going from point A to point B, we have to go pick up a passenger, which adds another action that we can take, plus getting towards the goal. So we have more actions. You can see that this is a larger environment, a larger map, so that there are more states. And because there are more states and there's more possible actions, this adds more complexity. And if you take this kind of thinking, this framework, and you look at some of the modern day examples of using this reinforcement learning, like auto self-driving cars, you can really tell how advanced and how much training and how complicated those problems are to solve when it takes a while to even go. And like it is quick to train this one. I think it took like 30 seconds, maybe a minute on CPU. But when you get to more complicated environments, um, you have to go mess with a bunch more variables and do a lot more training runs. So with that, that concludes our intro to Q learning. And I look forward to seeing you next week for Unit 3, which is an introduction to deep Q learning. So now introducing neural nets to assist in that Q table, Q function process. And we're going to be solving these Atari games. So definitely exciting stuff. All right. Have a good one.